In this video, I want to discuss topics pertaining to graphing and polynomials. So let me put a random graph of a polynomial, and I'm going to define some terms. All right. So we know that polynomials have they have natural number exponents, they have coefficients terms. You don't see ever a polynomial where you have a variable in the denominator, right? That was how we can discern if an expression is a polynomial or not. Okay, so this is a possible graph of a polynomial. And so what are some properties that we can define and analyze? So we can talk about the intercepts. Intercepts are referred to the points of the graph of a polynomial where it intersects the vertical and horizontal axes. So I will put green dots at the intercepts. If it intersects the horizontal or x-axis, it's called an x-intercept. If it intersects the y-axis or the vertical axis, it's called a vertical or y-intercept. Okay, so that's how you determine those. And also, we can talk about the maximum and minimum for the entire function or for a specific part of the function. Okay, so for this specific, let me put some red dots here. Can you see that those red dots are at peaks and valleys? So those might be the max and minimum for the well, there's only one max and min for the entire polynomial, but those for a specific little neighborhood, those are the maxes and mins of little intervals that include those. Okay, so the only thing I want you to remember is that the max and min just refers to the biggest and smallest value for a part or the entire polynomial, for the entire domain. Okay. Furthermore, the x-intercepts are also referred to as the zeros. Okay, the reason we refer to the x-intercepts as zeros is because if you wanted to find the x-intercepts, what you would do is you would solve this equation. Okay, so that's how we get zeros. Therefore, x-intercepts and zeros are related. Okay. By the way, to solve for the y-intercept, you simply evaluate what this is. Okay. So this gives the y-intercept. Okay, so we took care of intercepts, zeros, the maximum and minimum. Now, it's going to be useful to know how many terms a polynomial has. Okay, I'll show you why in a minute, but let me show you what I mean by a turn. So if you look starting from the left, the polynomial kind of turns to the right. So here is one turn, but then it starts turning the other direction. So here we have a turn number 2, and then it starts turning again in another direction, and then it starts turning again in another direction. So 1, 2, 3, 4 turns. Okay, now the reason that that's useful, one reason that that's useful is because of the following fun fact. The degree of a polynomial is one more than the max number of turns its graph can have. So this graph has 4 turns, so the degree is 5 or bigger. It's a quintic, as they say, or something bigger degree than that. Now, let me give you some other examples. A quadratic, y equals x squared. The degree is 2. Notice it has 1 turn. See how it's 1 less? A cubic, x cubed, it looked kind of like a sideways S, right? The cubic graph, that has 2 turns. So notice the degree is 3 and the number of turns is 1 less. Right? Now, the number of turns doesn't have to be 1 less. That's the biggest it could be. Okay, let me give you an example where it's not the max. All right, so think about, let me go to a new whiteboard. Think about the graph of x to the 4. what does the graph of x to the 4 look like? It looks kind of like a parabola. Okay, so the degree is 4, but the number of terms is 1. So the number of terms doesn't have to be 1 less than a degree. It has to be between 1 and 1 less than the degree. Okay, or 0 and 1 less than the degree. All right, so we've defined a number of terms. We've defined turns, max, min, intercepts, zeros. One more definition I need to address now. So let's talk about long-range behavior. Okay, long-range behavior refers to what's happening when x becomes huge, a huge positive, or a big negative number. Okay, so let me make a comment at the bottom of the screen. The long-range behavior, and I'm going to use this new notation I want you to get familiar with. The long-range behavior refers to the behavior of a function as x approaches a huge positive number. So I'm going to write it this way. Okay, what that means is x approach. Well, let me put both of them. Okay, that's my way to express the infinity symbol with a keyboard. So the long-range behavior refers to the behavior of the function as x approaches plus or minus infinity. Okay, now for a polynomial, that'll mean it'll either get really huge, a huge positive number, or it'll become a big negative number. Okay, the polynomial that I have on the screen, you would say that the long-range behavior as x becomes a big positive number, right here, let me circle it. So as x goes to a plus infinity, the function, or y, also goes to plus infinity. Okay, now let's do the other side. On the other side, let me switch colors. Let's do, how about orange for that one? So here is the left side. Okay, as x, the long-range behavior as x goes to negative infinity is that the function, or y, goes to negative infinity. All right. So now that we've defined some terms and I've shown you an example of how to get the properties related to those terms from a graph, let me now talk about how you can get graphs when you have an algebraic expression. All right. So the first thing I'm going to do is I'm going to remind you of our toolkit functions. So you should have memorized the graphs of these basic polynomials. Okay, the first one is linear, the second one, quadratic, is a parabola, and then the last one is the cubic, looks like the sideways S I was talking about. Okay, now, and so if you memorize those, remember that you can get other expressions related to those by remembering your transformations. So like 2x plus 1, you can get the graph of that, or minus 3x squared plus 5, and then for the cubic, minus x plus 7 cubed divided by 6 plus 10. All of these pink expressions are related to the toolkit, the simple ones on the left. And what do you do to convert the left graphs to the pink ones? Well, remember, there's stretching, compressing, shifting, reflections involved. Okay, so that's my first response to how you graph something without a calculator or a technology. Okay, and by the way, that is a way to graph using technology, but if you wanted to get a sketch without technology, this would be the first thing I would say. All right, and then let me close with this last question. What if you had something that was a higher degree? How in the world would you graph that? Okay, so for example, what if you had an 8th degree polynomial? Okay, well, suppose that you were able, I don't know what polynomial you have, but suppose you were able to factor it. Okay, so let's say the factor turned out to be the following. So this is a 4th degree, so this is bigger than the example that I was talking about. Actually, let's make it a 5th, let's make it a 6th degree. No, this is a 7th degree polynomial. Okay, and so let's say that let's say that we had this factored form. What in the world does the graph look like? Okay, well, using our properties that I've defined, we can get pretty far. Okay, you know what? Before I do this one, let me do a simpler one. Let me do the one without the exponents. Okay, and let me put a 5 right there, and so let me remove the minus from here. Okay, very good. So I'm going to do the black graph before I do the pink one. Okay, so here we go. First of all, can you see what the x-intercepts are? Okay, remember from algebra that the factored form gives you the x-intercepts. So the x-intercepts, the zeros, are -1, 2, -3, and 4. Okay, so we know that the graph has to cross those points. So that's already a big help, isn't it? So let's go ahead and put dots there. So the graph's got to go through -1, 2, -3, and 4. Okay, now we can also get the y-intercept. Let's plug in 0. What is y of 0? Well, plugging in 0, we get 1 times -2 times 3 times -4. And that gives what? -24, right? So that means that the dot, the y-intercept, is going to be way down here somewhere at -24. Okay? So now you can connect those points, and voila, we just did magic. We found the graph of a complicated high-degree polynomial. So between the part with the y-intercept is going to look like the following. It's going to obviously have to come down to the y-intercept and then go up, and then it's obviously going to have to bend down to go through the x-intercept at x = 4. All right, there you go. Now the graph has to keep going down. So I'm going to put arrows like that. Now, how do we know that it's not going to? Well, we know that it can't bend up and go through the x-axis because it can't have any more x-intercepts, right? So there you have it. There's a graph of that quartic, and now notice it has 1, 2, 3 turns. Okay, which a quartic you can have 3 turns for a quartic. So actually we know that we don't have more turns, so you might say, well, okay, it can't cross the x-axis, but couldn't the graph do this? Couldn't the graph, like on the right side, couldn't it do this dance below the x-axis? Well, no, because it can't have more than 3 turns, remember? So that's how we rule that out. All right. Now notice I've got mountains on this graph. Okay. So you might ask, well, how high are these mountains? Okay, the maxima for neighborhoods, including those peaks. All right. Well, for that you'll need to do more work. So this is just going to give you a sketch. All right. I can't tell you how high they go. You're going to have to plug in some numbers or do some other effort to get the exact values of those orange dots. Okay. Now let's now go to the pink example. Okay. So once again, we've got the same x-intercepts, so I'll keep those on our graph, and let me just remove the old graph. You might think, well, okay, so it's got the same dots, so everything's going to be the same, right? Hold on. So there, whenever the exponent 3 and the exponent 2 cause special things to happen at those zeros. Okay, this takes some care to explain. So because you've got a, let's do the exponent of 2 on the x minus 4 part. Okay, what that does is it causes the graph to bounce at that 0. Let me show you what I mean by that. In other words, you get a little mini parabola, because remember, an exponent of 2 is associated with a parabola. For the x minus 2 part, you end up getting a little cubic close to the 0 of 2. All right, so let me show you what I mean by that. So the graph comes down, and then it comes up, okay, and you kind of have a little cubic shape, okay, and then now you go down to the 4, and you're going to have a little parabola bounce, like that. See that? Okay, that's the adjustment you have to make for the those exponents. And then on the other side, you don't have any exponents at the minus 1, so that's just a normal intercept, and at the minus 3, nothing fancy happens there. Okay, so there's the graph of that. Now once again, we can count the number of turns to make sure we didn't make sure that agrees. So let's see, we have 1, 2, and remember the cubic part added another turn there. So we have 1, 2, 3, 4, 5, 6, and that agrees with our 7th degree polynomial. Okay, what about if you had other exponents? Now let me mention another thing. Okay, so what if you had like, instead of an exponent of 2, what if you had a different positive odd number? Okay, you will get the same mini parabola or bounce, whatever you want to call it, for exponents 2, 4, 6. So they're all going to give that same effect. Okay, you will get the same mini cubic for exponents 3, 5, 7, on and on. Okay, so how do you know whether it's a bigger exponent or not? Okay, well, in order to determine whether it's a bigger exponent, you're going to need to do some other work. Okay, maybe you know how many turns the graph has to have, and so that would put a limit on the biggest degree. Okay, so it'll take some other info, but just beware that you could have bigger exponents and still have the same effect. All right, now we can also go in the other direction. What if I gave you a graph and I wanted you to find the equation associated with that graph? Okay, that would be, if you understood how I plotted these complex functions, then you already understand how to go backwards. So from the zeros, you could get the factored form. From the y-intercept, you could get maybe either the coefficient in front or an additive term. Okay, from the number of turns and the behavior around the zeros, you could get the exponents. All right, so that would be exactly the reverse.